Hello and welcome to this IFT research call. Today, Leonardo from the Codex team is going to present on at the intersection of data availability sampling and shared mempools. Thanks, Leonardo, for doing this call, and the stage is yours.
Thank you very much. And thank you for the invitation to do this research talk. Okay, I'm gonna share my slides. Let me know if you can see them now.
Yes.
Yes, it works well. Okay, thank you. Awesome. So yeah, thank you everyone for attending this talk. This is a talk about the research that we are doing in collaboration with the Ethereum Foundation between the Codex team and the EF researchers. We have been working with the EF for about 2 years now, or maybe almost 3 years, on data availability sampling, which is kind of the next step in the roadmap of Ethereum for reaching scalability. And so, yeah, what I'm going to present here is first, I'm going to, kind of give a little bit of the background. What is the context? I'm going to talk about, why we need scaling into Ethereum. Then I'm going to talk about the solution that we came up and, what we implemented for it in the past. So I'm going to talk about, what we blobs that were implemented for Denem. I'm going to talk a little bit very briefly about what we see today after the Pectra fork that happened about a couple of weeks ago. And then I'll present the plans that we have for PRDAS, which should come in the next fork, which is Fusaka. And then I will present a couple of proposals that we, the Codex research team, is kind of pushing forward in order to, reach the scalability that we want in Ethereum. And hopefully some of those ideas can be implemented in Amsterdam, or maybe even before, hopefully. And then I will conclude and present, some of the, trade-off between the different ideas that I will present here. All right, so let's start. Okay, so yeah, all of these research started actually in 2018. I joined in the workshop to make Ethereum more scalable. At the time, Ethereum was saturated with CryptoKitties, and there was a clear vision that we needed to do something to increase the number of transactions per second and overall scalability of the network. And so at that time, we wanted to reach a point in which Ethereum can do way more transactions per second, but at the same time, we didn't want to give up on the other aspects that make a blockchain a real blockchain, which is one, decentralization, and the other one, security. So of course you want to have a blockchain that is secure, otherwise it's completely useless, right? If anybody can, cheat the system or introduce fake transactions or something like that, then the whole idea is not interesting. But it's also important to keep decentralization. And this one is a little bit more subtle and also difficult, because what we want is to be able to reach a level where the network can handle maybe 3 orders of magnitude more transactions than what we can today. But at the same time, the nodes that participate in the network do not need to be 3 orders of magnitude more powerful in order to participate meaningfully in the network. So this is what we what we struggle here is decentralization. So how to make things much faster while using the same, hardware and network bandwidth that we have today. That's more or less the objective of all this research. So in 2018, there was this vision of sharding that was proposed. I was at the workshop in Taipei where Vitalik and others presented this idea. This turned out to be a really difficult thing to implement in a kind of in a couple of years. So In 2020, there was another direction that was proposed, which was kind of a roll-up-centric roadmap, in which Ethereum will scale, through the through rollups. Okay, and I'm going to move a little bit fast at the beginning. I don't want to take too much time on the history, but yeah, I want, for those that are not very familiar, I wanted to give a little bit of context about what we are doing, what we are doing. Now, the problem of this is that rollups need a space. If you let's just imagine that rollups, work out there and they bring scalability to the network and to the entire Ethereum ecosystem. But at the same time, they need a space on the layer one in order to, kind of inherit the security of what we call the layer one. Okay. So that was a problem that we needed to solve. That brought us to what happened last year, which was the Deneb Cancun or Dencun hard fork. And so let me explain a little bit about what we did there. So, historically, we had this way to store data on the Ethereum blockchain. It's called cold data. And in there, the data is stored on chain, but it has several issues. One is that since you are storing the data in the layer one, say in the main Ethereum chain, is kind of there forever, and so that is kind of a problem. And there is another problem also, is that you have limited space. So if you want to store things on cold data, you only have a few megabytes at the most of storage per block. So that's another kind of throwback. And then the other thing is that it's kind of expensive storage. Okay, so I think you have to pay about 16 gas per byte in cold data, depending on whether it's a 1 or a 0. A 0 is a little bit cheaper. But anyway, it's kind of a expensive storage. So basically, you have three problems if you want to store your rollup data in cold data. One is time, because your data is going to be stored forever, and that is a problem, because then the size of the chain, of the blocks will grow too much if rollups are constantly putting data there. That is a problem. Then the other problem is space, because you don't have enough space, and then the cost, right? So time, space, and cost. So those are the three problems that we had with cold data. So to solve that, we propose Tinder. Blobs, which is kind of like the Tinder of Ethereum, because they solve more or less the same issue. If you don't want to, commit, with anything, if you don't like long-term commitments, this is what we propose. This is blobs. If you just want like a snack, a snark, you want to store your snarks from your CK rollup for only a limited time, just a few days, then you can use the blobs. So that's a better solution, because it's temporary storage, it's ephemeral. You only store data for 18 days. You have more space because you have up to tens of megabytes if we manage to scale the way we want. And also, it's an independent market, so it's different from the traditional gas market. So that's also an important difference there. So this was the way that we kind of, invented to solve this problem of storing layer 2 data on cold data to use blobs. And it kind of solved all those three problems. So we launched Deneb about a year ago, a little bit more than a year ago, and it has been working well. Here are some figures that showed how was the blob kind of data working at the time of DEF CON last year in Bangkok. So I took these figures from my presentation in DEF CON. You see more or less the distribution of how many blobs are used per block. So at the time, you could only have a maximum of 6 blobs per block, which is the pink part that you see here. So about 20 1% of the blocks had 6 blobs. About 41% had no blobs, and then you see the distribution of the others. What is interesting to see on the right side is that the propagation of the blob data was actually fast in all cases. And that was one of the concerns that we had because, traditionally, the blocks in Ethereum are about 100 kilobytes in size. This is kind of the average. It can go up to 2 megabytes, more or less, but the average is around 100 kilobytes. But now you are adding 6 blobs, and each blob is about 128 kilobytes. So you are kind of really increasing several times the size of the data that needs to go through the network in this 12 seconds that you have as the slot of Ethereum. And what we see here is that it's fine. All the blobs arrive within more or less 2 seconds of the slot. So basically, we have enough time to send all the data that we need to send in the very first few seconds of the slots. So that is good. That has been working quite well for over a year now, and that was all great. Now, what we have today, after the hard fork, the Pectra hard fork that happened on the 7th of May, we have a little bit more blobs. So yay, we got more space so that layer 2 rollups can store more data. And what I have here is a figure that compares the last 10 days before the hard fork in blue and the next 10 days after the hard fork. And what we see is the distribution of how many blobs per block did you see in that time. So in blue, you see that the maximum number of blobs per block was 6, because as I explained, that was the limit given in the specification. And we have moved that limit to 9, so that's what we see. That now, after hard fork in the Pectra, we see up to 9 blobs per block. And we see that some of the blue kind of slopes here, mountains that we see here, have kind of moved towards the 7, 8, 9 blobs per block hills that we see on the figure. Okay, so this is more or less how things have been changing in the last 20 days, more or less. All right, so that's good. We now have up to 9 blobs per block, and we are hoping that we can increase that up to 12 and maybe even 16 blobs per block in the next coming months. Okay, so that's kind of the context of all the research that we are kind of doing. Now I'm going to present what we expect to happen tomorrow, and this is also kind of old news for me and for the team that has been working on this research, because we have been working on this for already 2 years, as I explained. So what I'm going to explain now is what we call PRDAS, which is basically the next step after what we have running right now. So what the idea in PRDAS is the following one. Right now, every node in the network has to download all the blobs to check their availability in order to attest that the block is available. You need to make sure that the blobs in the block are available. So you need to download all the blobs. That's how it happens today. And then 18 days later, you can remove those blobs because the rollups don't need it anymore. They already kind of had enough time for the optimistic rollups to, raise a complaint if there was some error, and for the CK rollups, similarly, you had enough time to verify that the CK work was done correctly. Now, what we want to do is to guarantee that the block is available without actually storing the whole blob data. Okay, because we want to increase the number of blobs sufficiently in order to put even more and more data in the from rollups, and then in this way increase the number of transactions per second, and so on and so forth. So for this, the idea is that we kind of partition the data blob data into columns, as you see in the figure, and then every node has to download only a number of columns. So what is proposed today is that first, blobs are disseminated over the deep peer-to-peer network on the execution layer. So the execution layer nodes can download the blobs by pooling. So they say, okay, I want to download this blob. I don't have this one, so please send it to me. And they have their own blob mempool with the blobs in there. Okay. Now the CL nodes verify the blob availability, and then they can extend those rows through erasure coding. So you take the row, you extend this as a polynomial, and then through Reed-Solomon encoding, and then now you have the double amount of data. But this is going to be important for recovery, because even if you lose some of these columns or part of the data, through the Reed-Solomon encoding, you will be able to recover whatever data is missing, up to some point, of course. Now, so what we do right now is that we divide these blobs in 128 custody groups that we call columns. And so every node has to has to custody at least 4 of those columns, or 4 of those custody groups. Okay, so that means that they need to hold those 4 columns for the total period of time of the 18 days that they are supposed to keep the data from the moment the blob was included in the block. Okay, and then they also need to disseminate and propagate those columns over the gossip subnetwork. And then that's it. Once that is done, the execution layer client can erase the blobs from the mempool because they already have been included in a block. And then the consensus layer only needs to hold to 4 of those columns, so 4 out of 128. Okay, so that means that in reality, you are, for every block and blob data that you have in a slot, you are only downloading 1/32 part of the data. Okay, that's the minimum that you are required to download if you are an honest node in the network. Now, you are also allowed to download more data, more columns. And you can ask me why you could actually even store the whole data set if you want to. If you have the bandwidth and the storage for it, then you're allowed to basically download all the columns and keep them for the 18 days. That will make you a super node. We call those super nodes. Now you could ask, why would anybody do that? If I can save bandwidth, I can save storage, and I just need to store 4 columns. Why would I download the whole thing? And there are several reasons why you might want to do that. For example, one of those is you might be running a node that is working on a block explorer, and you actually need the blob data for showing it in the explorer or in your dashboard or whatever it is. Now, the other option is that you are running a node and you are part of the rollup, a specific rollup ecosystem, and so you want to make sure that you can easily access the rollups data, so the blobs. And so for you, it's very convenient to have all the blobs in your database or something like that. So there are many reasons why multiple actors in the ecosystem will be interested to run super nodes. But that's just optional. That's if they want. That's not a requirement. The requirement is you only need to download 4 columns out of the 128. So this is more or less what is coming with PRDAS. This is very, high level vision of what is supposed to come in the next hard fork, which is Fusaka. Let's see when it's ready. Okay, so this is what we have discussed and investigated. We have done many simulations in the Codex team to kind of support this vision. We have evaluated different trade-offs, etc., etc. Now, again, this talk is mostly educational and try to present a history of how the Ethereum ecosystem is trying to scale, but also present some of the ideas that we are proposing. Here, I'm not going to be presenting any results or demos or anything like that. That's not the purpose of this of this talk is more for educational, and we can also have an interesting conversation of the research ideas that I will present. Okay, so let's move to that part. So now I'm going to talk about the new stuff, which we have been pushing forward as the new changes that we think will make the Ethereum ecosystem more scalable and will help in the vision of scaling through more blobs in the coming months or perhaps years. So we expect this to be implemented maybe for Glamsterdam, which is the next fort after Fulu. But who knows? Maybe we can actually implement some of these ideas before, even if they are not introduced in the specs. Maybe we can start having implementations out there that allow us already to see and do some experiments to analyze how things behave in the real world. We already have a simulator. We actually have 2 simulators in which we have been testing many of these ideas. But again, it would be much nicer to have real network experiments to kind of corroborate some of the things that we see here. So the idea is to scale up to 256 blobs. And then, so that's about 32 megabytes of data before erasure coding. So you have a matrix like this, as you see in the screen. The 32 megabytes is just the blue part. So each one of these rows is a blob that has, that can be divided into 256 cells, okay? And then you can put 256 of these blobs, one under the other, okay? So these are just data points. And then you extend them horizontally, as I mentioned before, and then you get the red square that you see here on the top right side. But then you can take all of these and do the same erasure coding vertically, and then you extend to the bottom part of this matrix, okay? And that's and then from 32 megabytes, then you will move to 128 megabytes. And that's kind of a lot of data. If you want to upload or download that in 12 seconds for every node in the network, is not that easy, So that's we cannot simply just keep using what we have today. We need to do kind of data sharding. We need to do sharded custody and many other things. So to achieve this, the idea is to move to this 2D erasure coding. So right now we have 1D erasure coding, which is what I presented just before here in PRDAS. The idea is to move to a 2-dimensional erasure coding. The execution level nodes do not need to have all the blobs in their blob mempool. That's one of the kind of expectations that we have, that they do not need to download all the blobs in their mempool. And also, the other requirement is that the CL nodes do not need to custody the full blob data, of course, because again, that would be too much. And the whole protocol should be easy on network bandwidth for home stakers. That means if you have to propose a block, hopefully you don't have to send 128 megabytes of data to the entire network in order to propose your block. So that's kind of the idea, the objectives here. So for that, we propose 2 changes. One of the changes that we're proposing is blob pool sharding at the execution layer. What this means? It means that we want to shard the blob mempool so that the execution layer doesn't need to download all the blobs. It will only download a few of those, okay? Now the question is how to do it. And the way we are proposing to do it is to take the version hash of the blob and then compare that with the hash of the node ID. And if the last byte or half byte matches, then you download that blob. If not, then you don't download it. Okay, so here is an example. You have, for example, a type 3 transaction that is pointing to 2 blobs, okay, that you want to include in a block. each blob has a different hash. This one finishes in A, this one finishes in B. You have your own node ID, okay? You take the SHA of that, SHA-256 of that node ID, and you get a hash. And then if the last character of that hash matches with the blob, then you download it and you store it in your mempool. If not, then you don't download it. Now, what that means is that you will download about only 18 of the 256 blobs that can fit in a block. Okay, so that makes about 2 megabytes of data that you need to download. Today, we are already downloaded about 1 megabyte. As I said, today we are already running blocks with 9 blobs, which is a total of about 1 megabyte of data. Okay, so doing this sharded blob pool, you only need to double the amount of data that you download, but you are multiplying the number of blobs by a much higher number, because we are going from 9 to 256. Okay, so that's much larger. If you imagine that the network has about 8,000 nodes, which is, I think, more or less the size of the Ethereum network today, then by implementing this sharded blob pool, about every single blob should live in about 500 nodes, more or less. Okay, so that means for every blob that is out there, running in the network, about 500 nodes will download that blob, because the hash, the last character of the hash, matches with the last character of the hash of their node ID. Okay, so having every blob replicated in 500 nodes instead of the entire network is much more efficient in terms of how you use the storage of the nodes in the network, but it's also 500 nodes is quite resilient. It's very likely that you will be able to easily find the blob that you need if you have 500 nodes in the network with that with that blob. Okay, so that's one thing. Now, I think it's extremely easy, and I have discussed this with implementers and developers on the execution layer clients, and I think it's really easy to implement this today, even if we don't need it, even if we don't put it on the specs for PRDAS or for Fulu or even for Glamsterdam. I think it's really easy to implement, because at this point today, I believe the execution layer clients are not required to download the blobs. They are required to download the transactions, the type 3 transactions, but they are not required to download the blobs into their mempool. Some of them do it, some of them don't. It's already kind of sharded. And also, we have to remember that there are blobs that are not shared on the public network. They go through private links directly to the block builders. Okay, so I think implementing this today, is just a few lines of code in order to check whether the hash matches your hash. And then if it does, then you store it. If it does not, then you don't store it. I think it's something that we can easily implement today. And we could, start doing some tests in some test nets or something, or dev nets, to see how this looks like in a real network with many nodes. Okay, so this is the first thing that we propose, and that will lead to a network in which you have multiple nodes. Every node has the execution payload, which is this little scroll that I put next to the nodes. That's the execution payload. So every node will receive the execution payload, but that is fine. So you have all the transactions of all the type of transactions and everything, but the blobs, which are these little blue rectangles that I have next to it, every node will download a different type of blobs, because depending on what is the hash of their node ID, they will need to download different. So that's what you see, different order of lines, because they have different blobs on their mempool. But you see the numbers that you see in the parentheses here is just the hash of the node ID. What is, depending on what is the last character, then you will be downloading different blobs. So in that way, you are sharding the blob mempool in this way. Now, the second proposal that I want to present is the partial column dissemination on the consensus layer. So what we have today, as I mentioned, is that you take all the blobs, then you take the column, of all those blobs, and then you disseminate those columns, the full column over gossip sub. Now, if you have sharded blob mempool, then you will not have all the blobs for the block. Okay, so you will have some holes here, and that is fine. That is completely fine. What we need to do is to implement a way to disseminate partial columns over gossip sub. So instead of only disseminating the full column, we say, okay, well, it's fine. You don't need to have the full column to disseminate it. You can actually disseminate cell by cell, or you could also disseminate by batches. So I only have, for example, these 3 squares out of these columns. So I put these 3 squares together in a batch, and I send that batch over the network. And I say, like, okay, this is what I have for this column. You guys get the rest from someone else in order to get the full column. Okay, so this is what we call partial column dissemination. And this could, again, be implemented today. This is something that I don't think is particularly complex. We already have full column dissemination over gossip sub. I don't think it's really difficult to go from full column dissemination to cell level dissemination. And even if we want to be even, a little bit more to move forward faster, we could also try to implement batch column or send the cells by batches over the gossip sub network. And that could be something that we could start testing today. Even if it's not in the specification, we could already start implementing this as a feature, as an optional feature in the clients in order to run experiments in testnets and devnets. So how does this look in practice? So what happens is you get some blobs, not all of them, only some of them, because it's a sharded mempool. You extend them using Rich-Solomon encoding. Then you take the columns that you are assigned to share over gossip sub, and you send those cells through partial dissemination. Okay, and that is fine. You do this on one side. I see some question. I'm just finishing, so I will take the questions at the end if that's okay. So I see. So you have on the left node 1. He has these blobs, and then on node 2 you have a different number of blobs, but you have the same columns ID that you have to custody. Okay, so that means you're going to share these squares over the network, and on the other side, the second node will disseminate these squares, and the combination of those two nodes will make the entire column. Okay, so this is just a figure to kind of show how multiple nodes working together, disseminating whatever cells they have, will allow to any other node to reconstruct the entire column, and that is completely fine. Other nodes, you will have like different blob charts and different column IDs, and you will be sharing different net data over the network, and that is completely fine. But that will allow you to then reconstruct this entire full matrix, because you receive the blob, you extend it horizontally, you shared the partial columns that you have, you receive some from one node, some from another node, some from another node, you get the full column, and then you are now able to do a ratio coding vertically to recreate the bottom part of this figure. Okay, and that way you finally get the entire two-dimensional matrix that we had at the beginning, that we kind of put as objective at the beginning, and with a much more efficient network than what we proposed previously. So to conclude, okay, so in comparison, what we have today is a system where all the EL nodes download all the blobs for every block. Okay. On the other side, what we are proposing here is a system in which the execution layer nodes only download part of the blobs. Okay. That's a big difference, because that's much less bandwidth that you need to spend downloading blob data. Then you have the block builder or proposer that disseminates everything on one side of the proposal. But the new proposal is a proposal in which the block builder proposer only needs to send the execution payload. He only sends the execution payload, and the rest of the nodes will be the ones that will be disseminating the blobs, either rows or columns, partial columns. Okay. So the block builder does not need to send all the data. It could do it if it wanted, as a kind of a best effort, like, okay, I'm gonna do it, but slowly and later. Like, imagine the block builder is a home staker. Okay, you still want to be able to propose a block without needing to upload 120 megabytes of data in 12 seconds. Okay, imagine you live in a far country, and you don't have a great internet connection, and you still want to participate in the Ethereum network. Well, this is a way of guaranteeing that you can, because you only need to send the execution payload, which is only 120 kilobytes instead of 128 megabytes. Okay, so it's 1,000 times less data that you need to send. Now, this consensus layer nodes get rows from the execution layer nodes. So they have to custody the same rows. So basically, you say to the execution node, like, hey, give me the blob. So basically, you are just moving it from one part of the disk to another part of the disk. So you don't get it through the network. The CL nodes, and the other aspect, the CL nodes have to download both rows and columns, which is not great. In this way, okay, sorry, this is actually download. This is the EL nodes that download the rows, and the CL disseminate partial columns, and they download columns. Okay. On the left, you had a system in which you had to disseminate full columns. On the right, you have a system in which you disseminate partial columns. So this is kind of, I'm not sure it's very clear, but I was trying to put on one side the old version and on the right side the new version of the protocol, and was trying to compare these two things. Now, there are a few options here that I want to mention, and this is the last slide. After this, I will answer all the questions that are in the chat. Now, as I say, the block builder or proposer can disseminate all the data on a best effort approach, meaning that it doesn't need to, the data doesn't need to arrive, 12 seconds, within 12 seconds, actually within the first 4 seconds, if you really want the block to be taken into account. It can send it, but a little bit much slower, because actually most of the nodes will get the data from their peers, not from the block proposer. Okay, so it can be like kind of like a plan B in case the rest of the network is malicious. Like, imagine 60% of the network is malicious and is withholding the data. Then the block proposer can send the data, but this will be like a plan B, not the main path from which the nodes will get the data. We could also introduce mempool tickets. But honestly, here I think is not useful because the blob mempool is horizontally sharded, so you cannot really spam it easily, because it works more or less in the same way that already works today. You can also use I don't want messages to reduce bandwidth upon cell reception. So once you receive a cell, you send I don't want messages to your peers, and then they will not send you the same cell again and again and again. Now, since dissemination starts everywhere, we could use push-pull phase transition, and this is for the, this is very advanced. I don't know if people are familiar with the push-pull phase transition that we proposed a couple of months ago. But the problem with this push-pull transition was that it was kind of reducing anonymity for the nodes in the network. But through this strategy, since the dissemination starts from everywhere and not only from the block builder, then you kind of regain that anonymity again in the network. And this is kind of a nice feature there. Finally, the block proposer can change from sharded to full blob mempool temporarily. So this is a question that somebody asked me, like, if you only have part of the blobs and you have to propose a block, how do you do it? I mean, you will not have a vision of all the blobs that are out there, right? And this is not great. And that's true. But what you could do is that when you know that you have to propose a block, you know that in advance, at least one epoch in advance, so you have few minutes to say, okay, I'm going to change my behavior for 2 epochs or whatever, and I'm going to start downloading all the blobs. So I'm not going to have a sharded blob mempool, I'm going to have a full blob mempool for the duration of these 2 epochs in order for me to be able to propose a block with all the blobs that I want. Okay, and then after you propose the block, then you can switch back to a charted blob mempool. So you can have these temporary transitions when you need to propose a block, because you know in advance that you need to propose a block. So you can do that. And I think that's pretty much all. Thank you very much all for your attention. And I think now let me see how many questions do we have here. Okay, questions. Seeing the step from 1D to 2D, the naive thoughts that popped us, why a step at 2 dimensions, why not 3? No, that's actually a good question. We have analyzed the possibility to move to a 3-dimensional erasure coding. It's just, but looking at the numbers, it doesn't really bring much in comparison to what we have in 2D. It doesn't really increase the reliability level that much, and it does increase the complexity significantly. So it's not really necessary at this point, but it was analyzed, it was evaluated, and who knows? Maybe in the future we will want to move to a 3-dimensional erasure coding. That's a possibility, indeed. Okay, second, so my question is that plus, what is it about why it doesn't scale that way can help give some more intuitions about what is happening? Okay, so the thing about, okay, I'm not sure to completely understand the question, but if the question is about why we need 2D versus 1D, is about first of all, how easily you can recover the data. Okay, so once you have 2-dimensional erasure coding, you have way more ways to recover the data than if you have only 1-dimensional erasure coding. Basically, if you have 1-dimensional erasure coding, so only this part, if you lose this data here, so the erasure coding, the plus 1 cell, you will not be able to recover this blob. Okay, so you basically, if you have 50% plus 1 erasures, you will not be able to recover. Okay. In the case of the 2-dimensional erasure coding is different. Basically, if you have 25% of the data, so this square, the blue square, you are okay. If you will have to, even if you lose this row here, that as I said before, you can hopefully recover some of those cells using the columns where they are. Okay, so in terms of recoverability, you get a lot of much more reliability using 2-dimensional erasure coding. That's on one side. And on the other side, it also allows you to much more easily detect whether the data is available or not, because now you don't need to sample that much. If you have, and this is a simple probability a computation that you need to do. But after you sample 70 or 73 cells out of this matrix, you have like 10, the probabilities of the data not being available is like 10 to the minus 10 or something like that. It's like really, really, really low. So that's how having this 2-dimensional erasure coding help us also. It's not only for recoverability and reliability, but it's also is much faster to verify that the data is available because the sampling mechanism becomes much more efficient. Now, what are the incentives for nodes to store and propagate blobs? What happens if a node doesn't store blob data that is supposed to store? Does it get punished? If so, how? Okay, yeah, that's a great question. So this is something I didn't mention. You are supposed to store data based on your node ID. Okay, so you take your node ID. By the way, of course, your node ID is public. Everybody knows your node ID is disseminated over the peer-to-peer network. And based on your node ID, we can know what are the custody columns that you need, basically, what are the columns IDs that you have custody of. And the minimum requirement is 4 columns, as I said. If you store more, I will know which one are those, because just from the node ID, I will be able to compute deterministically, and anybody in the network will be able to compute deterministically that you need to store this column, this column, this one, and maybe this one, just by looking at your node ID. Okay, so what happens? I look at your node ID, you are in my PR table, and then I will be allowed to ask you for any of the specific columns that I know that you have custody of. If you don't send it, then I can decrease your score in kind of my reputation system, my local reputation system, saying, this guy didn't provide me the data that I wanted this time. And then I can ask it again and again and again. If you never provide me the data that you are supposed to have, then I will disconnect from you. Okay. So overall, using this mechanism, what will happen is the nodes in the peer-to-peer network will always try to be connected with those nodes that are always providing the data that they are supposed to have. And you know they are supposed to have it because the node ID is public. Okay. And if they don't, then you will be downscoring them to the point that you will be disconnecting from them. So what will happen automatically is that nodes that do not provide the data will be kind of kicked out of the peer-to-peer by the other nodes. That's what happens. Another question. Okay, let me try to do the follow-up before the other one. Are PIDs recyclable? What prevents me from saving bandwidth by not storing blobs? And when I'm disconnected, I just generate a new PID. Yeah, so you could do that. For that, you will basically need to erase your local information, and then you will probably need to relaunch your node, probably resync from 0, and then retry to discover peers in network. So it's feasible. It will take you some manual work, and it will take you some time to reboot the node. But yeah, that's something you could do. It doesn't sound like a really dangerous attack. I mean, what you are doing mostly is wasting time, but it's not really going to affect the other peers in the network. Most likely you will be kicked out very easily, and it's not going to affect. Most of the nodes are connected to 150 nodes, so one guy acting maliciously in that way is not really going to do much harm. Yes, I think raise hand.
Yeah, just also wanted to ask a follow-up on this. So with the peer scoring, like how do you integrate that? Because Gossip Sub would not be aware that a specific peer has to have this data, so there would be like some layer on top of that which hooks into peer scoring.
Yes, absolutely. So this happens at the consensus layer client logic. This is not implemented on Gossip Sub. So this is where you have to keep track of what are the nodes that are around you, what data they should hold, and keep track of those that provide data and those that don't provide data. Again, most of the nodes right now, I think Nimbus usually runs with 160 up to 200 nodes connected constantly. So there is a large variety of nodes to choose from when you need data. And if there is a node that is constantly ignoring you or failing to send you that you need, that is going to very quickly go to the bottom of that table and gonna get disconnected.
And how do you actually request that that specific data? So is this like a separate protocol, something like request response protocol, or like, just wondering how you put this on top of Gossip Sub?
Yes, it's a request response. Yes. There are two. There are one that is push. So there is the way that I got this column, I verify that is correct, and then I push it over my Gossip Sub topic, and that is just push base, and so you receive it from your peers and everything is fine. But there is also a request response, which is a pull base, of course, way in which if a specific node is not providing you the data that you want, then you can downscore it.
Do you use IFT, so like the Gossip Sub internal mechanisms, or is this something outside of Gossip Sub that you use to request that specific
So right now we already implemented I don't have in most of the clients. So I think Lighthouse already implemented, Prisma already implemented. I think Teco already implemented. Probably like the large majority of the network is already running with I don't have. Sorry, with I don't want. Sorry, with I don't want, which is once you receive the data, you can send this message for to avoid wasting bandwidth. And we are also working on I have, which is a way of gossip, which is I have this data. I'm not going to send it to you, but if you want it, you can ask it for. Okay.
Yes. Yeah.
Mhm.
Yeah, maybe I have a few more follow-ups, so maybe I would give the chance to others to also ask questions.
Okay, yeah, the other question is quite short. Yeah, thank you, Gur. Is there any other research direction using alternative to RS codes? Not that I think I know that this was evaluated at the very, very beginning. There was a little bit of research on what other erasure codes we could use instead of Rich Solomon. The standard in the industry all over, actually, not only on blockchain technology, but almost every industry is to use Rich Solomon because it's very practical, and it's also very fast right now. We have several libraries that manage to implement Rich Solomon encoding very, very fast, and so that's kind of it's kind of the most used out there. I know that we evaluated other type of codes, but Rich Solomon also has this property that is MDS, minimum distance, and so I think that's also very nice to have. I thought that property is kind of lost when you do it on a two-dimensional as schema as presented, but yeah, I think it is the best choice at the moment, given the libraries that are out there and how developed RS is in the system. But yeah, we did evaluate a few other options. It's possible that in the future we switch to something else if we find something that is faster and more reliable. But yeah, at the moment we are with Rich Solomon. And I think that's all the questions. You want to have more follow-ups, maybe? On the gossip aspect?
Yes. Yeah, for the normal question, I mean, yeah, one thing I also wanted to ask is, if on gossip subs you would only send columns or even parts of columns, but the full blob would not be sent over gossip sub anymore. I'm asking this because that will kind of change, gossip sub improvements that have been done so far, which were like, addressing very large messages. But now with this, you kind of break down messages, and then the actual messages that get disseminated over gossip sub will be small.
Yeah, so that's right. At this moment, what is used on the execution layer network to disseminate blob data, full blobs, is dev peer-to-peer. And I think that's working quite well there. But yeah, then from the execution layer client to consensus layer client, with this proposal, basically you don't need to send anything over the network. You just get it from local. And then you disseminate partial columns over gossip sub. As you said, partial columns are likely to be much smaller than the full blob. So it will not take advantage of those features that were implemented specifically for large messages, but I think it's definitely going to make use of other features that were implemented recently on Gossip Sub that are for other purposes.
Yeah, that's very, very interesting. Yeah, and I mean, these things, they could also be ported to dev peer-to-peer. There are also some efforts that people want to switch that to Gossip, like Unit 5, because there's only like a few differences. Would make sense to have like a similar.
Yeah, absolutely. There are some discussions about whether we should switch to Gossip Sub on the execution layer as well or not. I know that they are already working on Discovery 5. Previously, the execution layer was always working on Discovery 4. Now I think most of the implementations have already some. They are already working with Discovery 5. So I think there is a lot of transition going there. So maybe in the future, it's possible that blobs will be disseminated over Gossip Sub.
And one more question I want to ask, just to clarify, when you said like dissemination starts at several points, that's because blocks have been shared via on the execution layer, and then like there are several entry points where they like enter the gossip subnetwork.
Exactly.
Okay,
So the previous idea was the block builder sends all the columns and all the rows to everyone. And so, and the idea was to put a counter that says how many hops you have done. And after, I don't know, like 5 hops, you don't push the data anymore. You do only pulling. So basically you send an I have, as you mentioned previously, you send an I have, and if the other net peer still doesn't have that data, then it would request it from you. So that's what we call the push-pull transition. But the problem of doing that is that the one that sends you the column or the row with a hop equal to 0, then you know that that node is the block builder and the block proposer. Then that makes it very easily to kind of identify which validator is in which physical node, which is kind of dangerous because then there is no anonymity in the network anymore. Now with the proposal that I showed here, the columns will not arrive from one single node. They will arrive from all the peers you are connected with, because they're going to send you different parts of the column, and you are going to reconstruct it locally, and you are going to receive, pieces with hop 0 from several directions, and then you don't really know who is the block builder anymore. So that's how it keeps the anonymity.
Yeah, thank you. That's super interesting. I mean, the whole talk was very enlightening. Thank you.
Thank you so much. Awesome.
Yeah.
Thank you.
Yeah, thank you so much again for giving this presentation. I want to have a few more follow-ups. I need to read through that and then ask you. So it's actually super interesting. Thank you so much.
Awesome.
And also thanks to the audience for the questions. So this will be uploaded to YouTube. You can rewatch it. Yeah. And be free to post more questions into the IFT Research Call channel. And we will also have a forum post on the VAC forum, forum.vac.dev, with follow-up discussions on this. Yeah, thank you.
Okay, thank you, everyone.
Yep.
Thank you. Bye-bye.
Bye. Thank you.